In this video, we're going to calculate the effective magnetic moment for a complex where we've already determined the magnetic susceptibility at 300 Kelvin for the complex. It's going to be this copper tempo Hvac species. And so the chi measured that we have is negative 186 times 10 to the negative 6 EMU over moles. And this was at 300 Kelvin. And so the first step that we want to do to be able to determine the effective magnetic moment is determine the paramagnetic magnetic susceptibility. So to do that, first we are going to have to determine the diamagnetic contributions of the ligands and of the metal in each case. And so the first ligand that we'll look at is the Hvac ligand, which we can see right here. It's very similar to Hvac. The only difference is that instead of having CH3 groups right here, we have CF3 groups. And we can exploit that when we calculate the diamagnetic contributions that Hvac gives us, because we can utilize the Hvac diamagnetic correction that we already know from the table. So we can just use XD Hvac. And so if we then switch out the hydrogens, we can subtract out the hydrogen. So there will be 6 hydrogens that are going to be switched out for 6 fluorines. Another change that's going to happen is that we're going to lose then the contributions of 6 CH bonds and we're going to gain 6 CF bonds. So if we then look at the chart, we can start filling in all of these different values to calculate the diamagnetic correction that we're looking for. And so in the case of the Hvac, we'll get negative 52 plus 6 times 6.3 for the fluorine. We can then subtract 6 times 2.93 for the hydrogen. And so next what we're going to do is then we're going to add the contributions for the CF bonds. And so we'll have 6 times 3.1. And so the reason that I'm using 3.1 is because on the chart we don't have a corresponding value for CF bonds. However, we do have one for carbon chloride bonds, and because fluorine and carbon can be pretty similar, we can make the assumption that those bonds are going to have about the same amount of diamagnetic correction. And so then finally, we'll subtract out the CH bonds. CH bonds we consider to have a value of 0, so we don't have to include that here. And so all of this now will be times 10 to the negative 6 EMU over moles. And so all we've done really in this case is we've taken Hvac and we've substituted out the carbon hydrogens for carbon fluorines. And so then the diamagnetic correction that we should get in this case right here, once we've added it all up, is negative 88.78 times 10 to the negative 6 EMU over moles. And so that is the diamagnetic correction for one Hvac. And so I'm just going to clean out the palette real quick. And so the next thing that we'll want to work on now is this tempo derivative right here. And so looking at this, what we can see is that we have this carbon-nitrogen ring, so it's referred to as a piperidine. And so we can use those bonds, which are directly on the chart. Then we also have 5 carbons that are part of a ring, so we'll use the C ring values. We also have a nitrogen that's part of a ring, so we'll use the N ring values, and we can add all of this up then. And so in this case, the diamagnetic correction for tempo is going to be 5 times carbons and rings plus 4 carbons plus 1 nitrogen in a ring plus 1 oxygen plus 19 hydrogens plus the bonding within piperidine plus 4 carbon-carbon bonds, and so those 4 carbon-carbon bonds are these bonds right here, plus 12 carbon-hydrogen bonds, plus the bond between oxygen and nitrogen. And so if we now plug in the values in this case right here, what we'll get is 5 times negative 6.24 plus 4 times negative 6 plus 4.61, sorry, negative 4.61 plus negative 4.6 for the oxygen plus 19 times negative 2.93 for the hydrogens plus 3 for the piperidine, and then the carbon-carbon, carbon-hydrogen, and oxygen-nitrogen bonds will all be considered to be 0, and so they won't contribute to the diamagnetic correction in that case. And so if we add all of this up, what we get is negative 117.08 times 10 to the negative 6 EMU over mole. And so now we have the diamagnetic correction for tempo, so I'm just going to clean up the board again. And so now we have the values for tempo, we have the values for Hvac, we also have the value for copper 1, which is negative 12 times 10 to the negative 6 EMU over moles. And so if we add up all of these diamagnetic corrections together, what we'll get is that we'll have the contribution of the copper 1 plus the contribution of the tempo plus 2 contributions from Hvac, which if we add all of those values up gives us negative 306.64 times 10 to the negative 6 EMU over mole. So now we have our diamagnetic correction, we have our measured magnetic susceptibility, and so what we can do now is that we can then subtract from the measured our new diamagnetic correction. And so what we will get in that case, if we subtract that, is a value of 120.64 times 10 to the negative 6 EMU over mole. And so if we want to determine what the mu effective is for the species, we can then just simply plug that into our other equation. So we have that equation is the square root of 8 times chi paramagnetic times the temperature. And so if we plug in all of our values here, 8 times 120.64 times 10 to the negative 6 EMU over mole times a temperature of 300 Kelvin. And so this is all under the square root. What we get is a value of 0.54 Bohr magnetons. And so that's our final answer. And so if we were then to further go and plug that into the electron equation to determine how many unpaired electrons we have, we would see that we would have a value that's less than 1 electron, which kind of makes sense because what we're actually working with in this case with tempo is an organic radical. And so that unpaired electron is actually going to be distributed throughout the entire molecule. And so it won't really be localized enough to be considered a single unpaired electron. And so this is the value that we get, is 0.54 Bohr magnetons from this work right here.